So for that scattering, I have to bring some a picture which provides you an idea. Wait a second, we are talking about wave nature of light, but in general, you remember when there's a light shining, you have your finger there, you see on the screen, there's a nice shadow forming. So light is supposed to be linearly propagating. But I'm talking about the diffraction, the bending of the light. What are we talking about? So what I mean is it really depends on the relative size, relative length scale of the wavelength of the wave and the size of an obstacle. So this is a fundamental. And when we discuss about scattering properties, this relative ratio would matter. I mean, relative size. So here I depicted, okay, what about the scatterers such as air molecule or dust or sleep? So the size we can define as 2 pi r or r. So this radius. When they interact with the wave, so which is depicted wavelength. So we can define the relative size. So when we talk about geometric optics, or it's such as X-ray. X-ray has a very small wavelength. So this X relative to the object, then X-ray is just passing through, or it doesn't bend relatively. While when they become comparable, they are more likely to interact. Or if this wave becomes much, much longer than this particle size, the phenomena is different. We call it kind of specifically Rayleigh scattering. So I want to show a BG plot, which is a little complicated for now, but based on this relative size of a particle compared to the wavelength, if its wavelength is very small, like X-ray, relatively, then you can, or the object is so huge, then it's in the geometric optics region. And if the size of particle is longer, bigger than wavelength, such as raindrops, hair, and much bigger size, then we call it into a misscattering region. If it is smaller than the wavelength, such as drizzle and cloud, and we call it Rayleigh scattering. And if it's a particle size is really small, such as air molecules, such as oxygen, nitrogen, when it interacts with the light, they don't care. You consider it uniform, so negligible scattering. Okay, so this one is a reference, but at some point you will be confused about, hey, when does this geometric optics happen? When are the other kind of scattering happens? So this chart provides you that information. But we are more interested in the interaction of light with the biological entity, especially such as the cells. So what happens when the light hits the cell? Those who have done cell culture will understand when you look at under the optical microscope, you don't see much contrast. Unless you have to introduce a new kind of contrast mechanism, such as a phase contrast or DIC. Otherwise, you don't see much. However, what happens is light interacts with the cell, they will somehow interact. But that interaction now depends on the size, relative size of this object versus wavelength. So here I plot the size of the object. The cells are about 10 micron range. The cell nucleus, mitochondria are about 1 micron, which is comparable to the wavelength. And lysosome vesicles are about 700 nanometer. So these really goes to the realm of Rayleigh scattering, misscattering, and some of the collagen fibrils, macromolecules are smaller than the wavelength. So their interaction is in fact undergo misscattering. So what's really important in this? So it's actually complicated. So we have to go back to see this cellular organelles refractive index. you look at extracellular matrix, is a little bit higher than water, which is 1.33. Cytoplasm, same as kind of this. The nucleus, it can be even higher. Mitochondria and organelles are higher than even the cell cytoplasm, because what matters is changes in refractive index, the difference. And melanin even have a high refractive index. So in fact, what matters is optical scattering from the light interacting with this biological structure, such as cells and extracellular matrix. The scattering is the one which we can detect and provide a contrast and image for us. So we want to see what actually gives more scattering. In fact, if the size of the entity is bigger, there's more scattering first. And also delta N, changes in refractive index, such as this nucleus and mitochondria, are higher than the rest. So there comes more scattering happens. So primary scatters inside the cells, you can say, are nucleus and mitochondria and other organelles. So this one provides more scattering, which you detect as an image.